Okay. Sorry. Yeah. Okay. So in the last class, we were trying to get a voltage reference, and we have reached till this point now. So what we started with was, we thought that when we have a forward bias diode, we can sort of get a voltage that is sort of constant. But as it turned out, this was a CTAT voltage. That is, if you increase the temperature, the voltage drops with temperature. So to correct for it, we try to get a voltage that increases with temperature. And in that attempt, we pass the same current through n parallel diodes. And we saw that if we take the difference between these two voltages, I'll call this as the EB2. Now, if you take the difference between these 2 points, that was a PTAT voltage, right? So let me write it here. CTAT voltage was the drop of one forward bias diode, and the PTAT voltage was the difference between two diode voltages. And what did this simplify to finally? Vt ln of n, right? Where n is the number of diodes we have here. Okay. And we told that finally, if we add these two voltages with the right scaling factor, that is Kp, this will make sure that we have a fairly constant voltage with respect to temperature. And how do you find this gain Kp? Yeah. So you take the first derivative of V out with respect to temperature, and that's equal to 0. And from this, you can calculate what this value of Kp. And for the chosen values, we saw that Kp ln n is what, around 18, right? Great. So this is still in words. We still haven't developed the complete circuit. So let's see how we can make a circuit that can generate this final V out voltage, right? So for that, let me expand V out. V out is V CTAT, and CTAT is one diode drop. So that's the EB1 plus Kp times the PTAT voltage, which is the EB1 minus the EB2, right? So now if you simplify it, what do you get? EB1 times 1 plus Kp plus VEB2 times minus Kp. Okay. So basically what we need to make a circuit that can take one voltage, amplify it by 1 plus some factor, and another voltage by negative of that same factor. So do you know some simple circuit that can do this? Right. So basically, this is the gain of a non-inverting amplifier that you will make using an op-amp, and this is the gain of an inverting amplifier, right? So for example, if I take VEB2 and do this, let me ground it for now. And if this is R2 and R1, you know that at the output, this VEB2 will be scaled by minus R2 by R1. This is VEB2. Now we also need to amplify this by 1 plus the same gain. So what do we do? At the non-inverting, you apply the other input. So probably let me draw it like this. VEB1, right? So now VEB1 will be amplified by 1 plus R2 by R2, Okay. So here now, what is the value of Kp in this circuit? Sorry, R2 by R1. Okay. Now remember that we wanted to have this gain Kp, and this gain should be a constant, right? Basically, if you increase or decrease the temperature, this gain should not change, right? That's what we had assumed, right? When you took the first derivative of this, we assumed that this factor is a constant. Okay. So now the gain we have is R2 by R1. Can you comment on whether this will be independent of temperature or will it depend on temperature? Why? Right? So some of you might know already. So I mean, the resistors themselves might have some temperature coefficient, but if you make them using the same kind of resistor, say R2, what is it, which color? Yeah, say R2 changes to R2 times 1 plus delta, R1 will also change by the same factor. So if you take the ratio, it's going to be constant. Okay. So now let's put everything together and form the complete circuit. So let me just copy paste this. So this is my V out, and VEB1 is the drop of one forward bias diode. So I will do this. Down. Okay, this is one diode. Now VEB2, this fellow is the forward bias drop of n parallel diodes. And according to our definition, we need to pass the same current through those n diodes as well, right? So we'll have the same current source. Okay, so let me erase this. N diodes. And this is the final circuit, right? And these two are same currents. Okay. Now let me label these. This is VEB1. This is VEB2. So now what is this voltage? Assume we have an ideal op amp. That is also VEB1 due to virtual ground. So let me mark it here. This is also VEB1. Okay. Now can you look at the circuit and see if everything is fine, or do you think there is something still pending here? So let me probably give you a hint. Recollect that in all the discussion so far, we assume that the currents through these two diodes must be exactly equal, right? Now look at the circuit. So let's say I call the current through this branch as Ix. What is Ix? I1, fine. Now if I call the current in this branch as Iy, what is Iy? Yeah, so we have two parts now for the current, right? So one is this current, and you'll also have current coming this way, right? So the current here will be I1 plus this current. And what is the value of this current? You know the potentials at these 2 points. No, it is not VEB2 by R1. Yeah, either this potential minus this by R1, which is essentially the same as V out minus VEB1 by R2, right? Both are same, right? So this is basically V out minus VEB1 by R1. So the total current that is flowing here is this. Okay. Oh, sorry, R2. Yeah, right. By R2. Okay. So now what we have to do, we need to make sure that the same current flows in this diode as well, right? And what is the extra current we need to add? That is V out minus VEB2 by R2. We have V out here, right? We have VEB1 here, which is basically this node. So can you suggest something so that we can pass this current to flow in the branch. Where? Right? This is fine. So if I connect resistor R2, now this path will add this additional current, V out minus VEB1 by R2, and that will flow here. Okay. So if you add this additional branch, then both currents will now be equal. Is that okay? So this is the complete circuit. So with this, we can generate the required band gap voltage. Is that okay? So let me copy paste this for now. Okay. So let's see if we can simplify this circuit further. Can you stare at this circuit and tell me if there are some redundant elements here? Why is R1 redundant? Remember, why was this R1 and R2 in the circuit in the first place? We needed the gain, right? See, we need these two diodes for sure. That was the whole point. That's where we started with. We need this fellow also, right? Because this is what is giving you the required gain, and this is required to add the current. Now, what about these two current sources? Okay, let me copy the currents in the branches also. Okay, let me write it here. So Ix is what? I1 plus, I'll call some I0, okay? Right? These are the two currents. Now we already have the currents provided by the op amp, right? And which means we don't have to have these current sources, right? The whole point of having this current source was we wanted to make sure that the diodes were forward biased and the currents must be equal, right? So in this equations, even if I1 is 0, the diodes are still carrying a constant current and those two currents are equal. Okay. So these two current sources, you don't need to have these two current sources. That's what I'm getting. If you have, it's fine, but it's not needed. Okay. So this is the final reduced band gap circuit. So let me redraw this slightly in a format that you will find in textbooks. So I'll start with the two diodes here. One, and I have the N diodes. Okay. And in series with this N diodes, I have a resistor R1, and it goes to the virtual ground. Okay. So maybe let me copy it here so that it's visible, right? So I'll have this resistor R1. So that is this is done, and this goes to the virtual ground. And even this diode directly goes to the non-inverting terminal, right? So we'll plus and minus, and then you have R2. Sorry, no. This is R2, and you have the same resistor R2. Okay, so this is the final output voltage we want, and this is approximately equal to your band gap voltage. Is that okay? Fine. Great. So, and yeah, this is obviously not the only way in which you can make the band gap circuit. The principles are still the same. We need to have the CTAT and PTAT voltages, and we need to add them appropriately. So let's see one other variant. And for that, let's actually look at this circuit once and try to understand it from a different perspective. So we know this voltage is VB1, and this is also VB1. I'll call this drop as VB2. Now, what is the voltage drop across the resistor R1 in this polarity? VB1 minus VB2. And what kind of voltage is that? It's a PTAT voltage, right? So I'll call it VPTAT. So let me write it also. That's VEB1 minus VEB2. Now, what is the current through the resistor in this direction? It's VPTAT by R1. Right? So this is basically a current which has the same property as a voltage, right? So now the same current will have to flow here also, right? Because the op amp doesn't take any current. Okay. So if I call this current as IY, IY is IPTAT. Is that okay? So how can I write V out? V out is the drop across R2, okay, plus this voltage. Is that fine? So this is basically IPTAT times R2 plus VEB1, right? I mean, that's basically what we had earlier also. This is our PTAT voltage, CTAT, which are added appropriately. Okay. Now, if you think about it, IY is equal to the PTAT current because you have forced this voltage to be equal to VEB1, right? Because this voltage is VEB2. The op amp has forced this voltage to be VEB1. And that is what is making the voltage across this resistor to be a PTAT voltage and the current here to be a PTAT current. Okay. So this is possible because, I mean, I'll call this voltage as Vy. So because Vy is VEB1. Okay. So now, in principle, if I have a PTAT current flowing through R2, okay, and I have the same circuit. Basically, whatever I have in this branch, I am redrawing it here, okay, and I force the current here to be VPTAT, and this is the same resistor R1, and this is the N diodes. So if I call this voltage as Vy, what do you think this voltage will be? So let me take a step back. We saw that if this, I mean, this current IY is IPTAT because this voltage was forced by the op amp to be the diode drop VEB1, right? So what I'm saying is, I'll invert the problem. Let us say I can generate this PTAT current somehow, this current, okay, and make it flow through this branch, right? I mean, if you think about it, all the circuit is doing is this op amp is providing the current, this PTAT current, right? Now let us say I somehow generate this PTAT current and make it flow through this branch. So now can you comment on what this voltage will be equal to? No, it's no, please. This I mean, I'm looking at the voltage here, right? I mean, if I have to draw parallel, this point is this, right? This voltage is our V out voltage. VEB1. Is that clear? I mean, if you think about it, this voltage, if I call it some VZ, what is VZ? IPTAT times R2 plus Vy, right? And that is same as what you have here, right? And we already have ensured that the current here is PTAT current by forcing this current here. So this voltage, what will it be equal to? VEB1. Okay, I mean it is simple, KCL using substitution theorem, right? So this is VEB1. I mean, right? If you have an element which has a voltage current I in a circuit, I can always replace it by a voltage source with the value V, and KCL and KVL will make sure that the current here is I. Okay, because KCL and KVL has to be valid in all the circuits. If you have not disturbed the rest of the circuit and you replace this element by an voltage source V, then KCL has to be satisfied and it will enforce the current to be I. Something similar is what we are doing here. We were doing a lot of things and making sure that this current is PTAT current. Now I turn the argument around and say that if I somehow make sure the current in this branch is PTAT, then this voltage will be equal to this voltage, right? These two will be identical. Is that okay? So let me draw this again. This is my some current IY, and say I make it equal to PTAT current and force it through the resistor R2, and I have R1 in the end diodes, right? This voltage will be equal to VEB1. So let me write it here. If IY is equal to IPTAT, Vy is VEB1, and you can tap this voltage directly and call it to be your bandgap voltage, right? But obviously, you can't exactly find what this current and make a current source with the exact same value, right? So let me write that here. What is IPTAT? IPTAT is VEB1 minus VEB2 by R1. Okay. Now, in general, if this current is IY, if this voltage is Vy, and this is say VEB2, what is IY? I mean, in terms of these voltages, Vy minus VEB2 by R1, right? Again, it's the same thing, right? If I make sure IY to be equal to IPTAT, this voltage becomes equal to VEB1, right? But as I mentioned, it is not possible to exactly find this value of IPTAT and have a current source which produces the exact same current, right? In practice, the current will be slightly different. So we cannot have a fixed IY. So what should we do? What kind of current source this must be? Sorry? I mean, it is a non-ideal current source, but I mean, what I'm saying is if you have the non-ideal current source, you can't get the exact value, right? So in practice, what would you do? I find that this current is not what I want, right? I mean, let's say you're in a lab setup, right? You, connect a current source. But if this current is equal to IPTAT, this voltage Vy will be VEB1. Is that okay? But let us say this voltage is not equal to VEB1. So what would you do then? Sorry? Yeah, I mean, let's say feedback is the thing, but in a very simple words, what would you do in a lab? You have a current source. I know that if the sorry, right? Basically, it cannot be a fixed current source. You keep changing the current until Vy is VEB1, right? So basically, you need a variable current source. Okay. So this cannot be a fixed current source. This has to be a variable current source. And how would you vary the current source? I mean, based on what would you vary this current? Yeah, you basically need to compare Vy with VEB1, and depending on Vy is greater or lesser than VEB1, we can go and tune the current, right? So basically, tune Iy to make Vy to be VEB1. Okay. Now, from these two equations, tell me if Vy is greater than VEB1, which current is higher? Sorry, Iy, right? Is that okay? So if Vy is greater than VEB1, Iy is greater than what you actually want. So what you need to do? You need to reduce Iy, right? So which implies Iy must be reduced, and vice versa, right? The same holds good in the other case also. So we need to compare Vy with VEB1, and we know how to generate VEB1, right? We pass the same current through one diode. So for now, I'll assume that we have it generated, and say it is a voltage source, VEB1. Okay. So I'll have to compare these two. Right? And then tune this current source, right? And what is the simplest? I mean, basically, this is not any kind of variable current source. You need to vary this current based on this voltage, right? So what kind of element is this? It's a voltage controlled current source, right? So Iy has to be voltage controlled current source. Is that okay? And what is the simplest voltage controlled current source? You know, it's a MOSFET. So what I'll do, I'll replace this by MOSFET. Okay, and let's say call the gate voltage as Vg. Now you know that if you have to reduce the current Iy, which is the current here, what do we have to do to this gate voltage? Decrease or increase? Increase, right? PMOS gate increases, current decreases. So which means Vg must increase. Is that okay? So the point is, if Vy is greater than VEB1, we need to increase Vg. So this is Vy, this is VEB1. Now can you tell me which should be the positive and which should be the negative sign for the op amp? Right is positive, left is negative, right? Because now if Vy is greater than VEB1, this voltage will increase, right? So I can go and directly connect it like this. Okay. So what this is doing, it is basically comparing Vy with VEB1 and controlling this current source, current value of this current source, to make these two voltages equal, right? And if the op amp has infinite gain, then you know that these two will be exactly equal. Is that okay? So let me draw that again. So we have control source, R2, R1, and N diodes, and this is VEB1, this is Vy. So I have to compare these two and fix it like this, right? Now the only pending thing is how to generate VEB1, and that is basically the forward bias voltage of one diode, right? So I'll have one diode, and of course, the current through this diode must be same as the current in this branch. So what do you suggest we do? So basically, I'll have one more CMOS. Right, so I'll do this. Right, so now for both the PMOSs, the gate voltage is same, source voltage is same, the current will also be. Okay. So now Vy is now VEB1. So the current here is the tap. So if I tap this voltage, what is it? In terms of the current and the voltage, what is V out? Sorry? Yeah. IP tag times R2, that is this drop plus this voltage, right? That's what we also want. Okay. So this is basically another way of generating the same bandgap voltage. Okay. Great. So yeah, so this is one commonly used variant of bandgap, and it turns out this has some issues in practice, especially modern designs. And one main problem is the following. We know that this gives you a bandgap voltage, right? So let me, yep. V out is equal to the bandgap voltage, and what is the value of this approximately? 1.1 to 1.2, right? So I'll just say 1.2 volt roughly. Okay. Now, if this voltage has to be, so basically this node is at 1.2 volt. So can you comment on how much this supply must be? It should be greater than 1.2 definitely, right? So VDD must be much greater than 1.2 volt. Okay. So and in modern designs where we have supplies of less than 1 volt, it's not possible. Okay. So the main problem is it has issues with, I'll call, low VDD, right? And yeah, and another thing is sometimes you may not exactly want to generate this bandgap voltage. We might want to generate, say, a fraction of this. Sorry. Yeah. So basically, this will not be exactly 5 volt. So what we'll do is we'll generate, let's say, 1 volt or 1.2 volt VDD from some other circuit. And how we'll generate it, that is also based on this bandgap. I mean, we'll discuss it probably later. Now, assume that we have the supply of, say, 1.5 volt or whatever. We have to generate this 1.2 volt bandgap voltage. We need a higher VDD, right? So let's say we have it for now. Okay. So yeah, so the problem here is the at say 1 volt or less than 1 volt supplies, we can't use this circuit. And it turns out in some cases we might also want to generate fractions of bandgap. For example, we might want V out to be, say, bandgap by 2 or say by 3 or something. Okay. And it turns out if you generate this, things become easy because let us say if I make a circuit that makes, I mean, generates VBG by 2, this, what will be this voltage? 0.6, right? Now we can see you can easily accommodate a supply of 1 volt. Okay. So that's why this kind of circuits which can generate fractions of the bandgap voltage is useful at lower supplies. So let's quickly see how we might do that also. So we want again the same thing. V out should be VEB1 plus KP times. This gives the bandgap voltage. Now let us say you want a fraction of this bandgap voltage. I'll call it some G. Okay. Now this is the required output we want. Now in this circuit, what is Kp? R2 by R1, right? So you see that any kind of gain you want, we generate it based on ratios of two resistors. That will make sure that that gain is constant and doesn't change a lot with temperature. Okay. So then similarly, even for generating this gain G, we'll realize it using ratios of two resistors. I'll call it, say, some for now, let's say Rx and Ry. Okay. Plus I know Kp is R2 by R1 times VEB1 minus VEB2 by G. Okay. Now, I mean, this portion is simple because instead of having a resistor R1, I can have a resistor G times R1 that will realize this portion. Okay, that's fine. So I'll probably write it like this: R2 times G times R2. Right? So now if you look at this one, we'll look at these two terms which are bracketed. So this is basically a current that is that has CTAT property, right? You know, VEB1 is a CTAT voltage. So what I'm basically doing is generating a current that depends on it. And here I have a PTAT current, right? We know how to generate this current. If we can somehow generate this current also and add these two currents, and now I can make Ry to be equal to R2, right? So which means now this is simply the CTAT current times the PTAT current times R2. Okay. And here the value of gain, what is the value of gain G in this expression? Rx by R2. And this is basically the fraction of band gap voltage that you want, right? And similarly, here we have R2 by R1. And what fixes R2 by R1? In the original circuit also, what fixed R2 by R1? The temperature dependence, right? You wanted zero temperature coefficient. So you differentiated whatever and you found value of Kp, right? So this is the value of Kp you need. And this is based on the zero temperature dependence. Okay. So let me copy this and see how we can modify it. So all these things. Again, if I call it VEB1, this is VEB1, and we need to generate something like this. Okay. Now, how do you generate this current? I have VEB1 here. This is VEB2. What change should I do to this circuit so that I can, the R1, I'll simply make it as G times R1. Okay, so this becomes R1 times G. That will make sure this current is the required PTAT current for now. Let me run here. Now, how do I generate this current? I need a current VEB1 by Rx, where, okay, see, here we have VEB1, right? So here, if we can add a resistor Rx, the current flowing here, this is CTAT, is the required CTAT current. Okay, so now we have PTAT current flowing here, CTAT current flowing here. So the current flowing here This sum of the two, that's what you want. And we wanted these two currents to flow through a resistor R2 to generate the voltage, and you have that here. Okay. So let me dot here. Yeah. So now again, stare at the circuit and see if is it fine or are we missing something? Sorry. We have to no, right? It's with respect to ground, right? Yeah, yeah. I mean, that is correct. Yeah. So basically, both of them are pointing out is we wanted V out to be the CTAT plus PTAT times R2. But what we are generating is, this is the total current. Let me call it I total. This is the total current. But V out here in this circuit, this is what we need. Needed V out is this. In the circuit, V out is what? I total times R2, that is this drop, plus a VEB drop. Okay. So it's not completely done. So what we'll do is, I'll take this resistor out. Now this is the total current. So let me probably copy it. So I'll copy this current to some other branch. Now this current is also the total current. And here I'll flow the current through an R2, and the other end of R2 is connected to ground, right? That's the only thing that was missing there. In the earlier case, when you had the resistor R2, here, the bottom end of R2 was connected to VEB1, and that's not what you want. Okay. Okay. Now again, look at the circuit and tell me if you find something missing or things are fine. Again, look, think about the original, circuits we had. We started with having two diodes, and we wanted the currents in the two diodes to be exactly equal. Now, here in this circuit, the current here is VEB1. I mean, basically here you have this current, but you also have drawing another current here, right? So what you can do is add the same, okay? Because earlier, even though the currents in these two parts were equal, this current, a part of this current was stolen by this resistor, and only the remaining current was flowing through this diodes. Okay, so you make sure you have one more branch which steals the same amount of current. Fine. So now this is our final V out, and this will generate fractions of the band gap voltage. And for this reason, this is called the fractional band gap reference. Okay. So just one last point about band gap. So here, if you know, I mean, lot of variables are there, and to a first order, you know how to find the values of these resistors, right? Because you know R2 by R1 dictated the gain to have zero temperature dependence, and all these Rx and all were dependent on the fraction of the band gap you want. So there is one other choice you can make, which is the value of n, right? And it turns out that often the value of n you choose is 8. we'll see why it makes sense. Okay, so basically what we want is one diode and 8 of them, right? Now, finally, when you physically lay these diodes, there are multiple ways in which you can place them, right? So, for example, you can have this as the one diode, and I can have 8 of them placed like this. Okay. Now, do you think this is a good choice, or do you think this might have some issues? Yeah, you guys have done layout before, right? So you guys know. Okay. See, finally, if you take any IC, right, you will not have the same environment throughout the IC. For example, you will assume that your P substrate is doped with something, with some doping concentration, but you'll always have some kind of a profile, right? For example, towards the left, you might have a larger doping concentration, and as it might decrease as you go to the right. Or in another example is on the chip, along with the band gap, you might have some other circuits. Okay, and let's say you have some circuit here, and that is consuming a lot of power. So which means the temperature around this region will be higher, right? But temperature towards the right end, that will be lower. Okay, and all our like analysis was based on the fact that all these diodes were identical, which means even their operating conditions must also be very identical. Okay, so placing all the diodes like this is not a great choice. So the usual thing that is done is the following. So you place, say, the first diode like this. This is the one diode, and you place the remaining around this. Say I'll call it N1, N2. Okay. Now let us say there is some gradient. Like it can be temperature or any kind of gradient. So let us say this portion has a higher temperature compared to this, right? Now you see that the diodes on this side will have a higher temperature than the average. This will have a lower temperature. So on an average, you see the temperature will match the ones at the center, right? So this way you kind of make sure that on an average, the operating conditions or the operating environments for all the diodes are kind of equal, similar, right? Because all we want is the one diode and all the 8 diodes to be having the same condition. Now this one diode is at the middle, like it is kind of at the average, right? Now here you have some diodes which have higher temperature, some have lower temperature. So on an average, if you sum up all 8, they'll match this guy. Okay. And this will be a very recurring theme in circuit design, right? Because you'll often find you can't have two quantities to be matched exactly. So the next best thing you can do is try to match them on an average. Okay. I mean, you might have seen in, you'll see in many kinds of circuits later also. Yeah, and this is what is done in practice. And now it might make sense why you want to choose N to be 8, because totally then you will have 9 diodes. So you can place them properly in this kind of a symmetric fashion. Okay. No, this is not the dummy diode, right? See, in the actual circuit, we wanted 1 and 8. Totally, we want 9 diodes. Okay, so this is the diode 1, and these are the, I'm calling N1, N2 to N8, right? Yeah. And that's why you place this diode here, right? It doesn't make sense to place this diode to the corner, because you want the sum of all these 8 to kind of match the operating condition of this guy. So that is why you make sure this is kind of at the center, like here. So if you have any kind of gradient in this direction or in this direction, it kind of averages it. Okay. So if you want, sorry. Yeah, okay. See, that's what in general, that's why you choose it to be like this. So that total is some n square, I mean, k square, right? If you have 9, 16 like that, it's easy to place them like this. But yeah, sometimes, let us say for some other application, let's say you want to have 10 of them. What you can do, let's say you place them like this. Basically, you form a 4 cross 4 array. You choose some of them as the 10 and have the others as dummy. Basically, they will be additional. They will not be connected to the circuit, but they are just there to make sure that the operating environments for all of them are identical, right? So, for example, let's say you might choose, these are 8, and let's say one here and one here might be the actual ones you want. So this is basically 10 elements, and all of these might be dummies. They are there just to make sure that the operating environment is same. So, okay, so let me point out one other issue, practical problem with Bandgap. For that, let's look at the simple circuit we had initially. Okay. So let us say you don't know anything about Bandgap, and for the first time you are encountering the circuit. Okay. How do you go about solving this? For any circuit, what would be the procedure you follow for solving it? Yeah, voltages and branch currents, you use KCL, KVL, right? And of course, some things you know because you have the same MOSFETs here, with the same gate and source voltages. If this current is I, this is also I, and you have the op amp, and the op amp in negative feedback will enforce these two voltages to be equal. So this is VEB1. So let's say this is one. Okay, so I'll call this VY. We know that EY is EB1, right? And in terms of the current I, and this is say the EB2, can you tell what is VY? I want to find the node voltage VY in terms of this branch current I, and I call this diode voltage as VEB2. Okay. And we also know that VY is VEB1. So I'll put it like this. And you know the IV relation for the diode. So this is basically VT natural log of I by IS plus 1. And for VEB2, what is the relation? I by NIS, right? Because 1/n of the current is flowing. You can think of it like this, right? So you can simplify this. So if I take this right here, what I have IR1 to be equal to VT ln of 1 plus I by IS, right? Now, if we know that the diodes are forward biased, then you can ignore this one, and you will get the solution. What is the solution for I? VT ln n by R1. Fine. I mean, that's what we had earlier, right? So the current here is the PTAT current, which is the PTAT voltage divided by the current. Okay. Now, can you stare at this equation we have? And can you think of any other possible solution for this equation. Yeah, I mean, it's a trivial solution, right? If we have I equal to 0, LHS is 0, these two guys go away, ln of 1 is 0. Okay, so you also have another solution, basically I equal to 0. Okay, and this is something you can expect with any kind of nonlinear circuits or nonlinear equations, right? If you have a linear set of equations, you can have at least, I mean, either one solution or infinitely many solutions, right? Basically, two lines intersect at one point, or like exactly parallel. If you have a nonlinear set equations like this, say you can have two solutions like this, right? So you shouldn't be surprised if we have multiple solutions for these kind of nonlinear circuits. And this is the required solution, but you also see we have one other possible solution. And it is an equally valid solution, right? If current is 0, what is this voltage? If the voltage is also 0, so this is also 0. So it looks like virtual ground is enforced. So what will be this voltage? Let's call this VDD. This will be at VDD, right? So for the PMOS gate and source are at VDD, so no current flows. So looks like everything is consistent, right? So if you don't do anything and just make this circuit, it is possible that finally you kind of end up with this dead solution. Okay. But it turns out that this is not a very stable solution, because say I inject a small current at this node. Okay. What will happen to this voltage? Huh? It will increase, right? If this voltage increases, what will happen to the output of the op amp? It will decrease by a lot, right? It will decrease. If this decreases, can you comment on the current through this? There will be a non-zero current flowing through this, right? And the only non-zero current you can have is this fellow, right? Because that is the only other solution possible here. Okay, so it turns out that this all zero solution is an unstable or a metastable operating point. Okay. But it doesn't mean that you let the circuit like this, right? Because it is true that if there is some minor disturbances, the circuit will wake up. Right? For example, if you switch off and on the supply, because of some disturbances, some voltages will change and the circuit will be alive. But you don't want that, right? Every time you want to make a call, you don't want to switch off and on your phone, right? So you need to make sure you have some circuit that kind of takes this up. So again, there are multiple ways in which you can do. One simple way is, let me copy paste this. As I just mentioned, if you pump in a small current, the circuit will wake up. But after the circuit wakes up, you don't want to pump the current, right? Because after that, you have this operating and you don't want to disturb any of the currents in the branch, right? So I want to use a current source. So you can use an NMOS or a PMOS current source. But all I want is once this voltage increases, I want the current source to be off. So which one do you think is a better choice? PMOS or an NMOS? PMOS? Okay, I mean, here by this, the gate is not connected here, right? The gate you might connect to some voltage, say VB. Okay, I want to make sure that if this voltage increases, the current source must turn off. If you have a PMOS, I mean, you have a gate to source voltage already, it will keep pushing the current. But for the NMOS, the gate is at some fixed voltage VB. The source will start increasing. And once the source increases, the NMOS will turn off. Yeah, I mean, a better choice here will be an NMOS transistor. Correct. Meaning this current source must turn off once the circuit is active. Okay. I mean, this is similar to, like, I mean, let's say you don't wake up early in the morning. What do Indian parents do? Huh? Throw water, right? And wake you up. But after you wake up, they don't keep throwing water at you, right? The same thing. Once the circuit is alive, you don't want to, like keep pushing it. So, I mean, this kind of circuits are called startup circuits. And of course, you can do multiple things. For example, you can sense this voltage and then push it down initially, and then like multiple combinations are possible. Yeah, I mean, it is not in saturation, right? If the source voltage is higher, basically, if the gate to source of this becomes less than the threshold voltage, transistor cuts off, no current flows. I mean, this is a very simplistic circuit. You can do multiple combinations. Just give an idea, that's all. Okay, so this is all about band gap reference. So now we sort of know how to generate a fixed reference voltage. So let's say you generate a full band gap of 1.2 volt, right? And let us say I have a circuit, a receiver block, let us say, receiver chain, that also needs to be powered at the same 1.2 volt. Do you think I can connect the entire receiver chain like this to the band gap? No, right? Because see, this is our output voltage. We cannot simply connect, like some other block, right? Because that will disturb the currents flowing in these branches. Okay, so you cannot do. So you cannot directly connect, this output of the band gap as a supply to any other system. But that is, let us say, that is the actual supply voltage you want. Okay, so this is the actual supply voltage I want, but I find that the band gap cannot provide the current for the system. So what do you do? What is the simplest solution? Huh? Yeah. You put a buffer, right? And what is the simplest buffer, Huh? Yeah, I mean, let's not go to transistors, right? It's very ideal. I mean, like you told, you can have an ideal op amp like this, right? And I'll connect this VREF voltage. I connect it. Now this can be connected to this supply of whatever circuit you. Okay. And of course, in practice, you will need, say, a supply of K times VREF. The K is greater than 1. So what would you do? Right? I mean, basically, instead of having a simple buffer with a gain of 1, we will use an op-amp based circuit which amplifies this voltage, right? And the simplest one, is the non-inverting amplifier. So what you can do is this. So I can have the resistor here to be K minus 1 R and this to be R. So if this is V out, what is this voltage? No, we cannot. V out by K, right? So I know this is VREF. If I connect these 2 points, the op amp will ensure that VREF is feed out by K. So we get the required voltage. I mean, this is basically a non-inverting amplifier, right? Gain of 1 plus K minus 1 R by R, which is K. Okay. So of course, now you can connect this like this. This is a very good solution. And of course, the op amp will need some supply like this. Okay. Now, even if the supply to this op amp varies, the output voltage will be constant, right? Because the band gap voltage is fixed, and all the op amp is doing is forcing VREF to be equal to V out by K. So as long as the op amp is providing enough gain, even if the supply voltage changes, the output is fixed. Okay, so this kind of circuits which kind of regulate or keep the voltage constant are called voltage regulators. Okay, and this kind of a non-inverting amplifier based configuration is a very simplistic method of realizing a voltage regulator. Okay, but as it turns out, this is not a great solution, although it works. Let me explain that. So this is K minus 1 R and R. Here, okay. And here is where I'll connect the circuit that needs to be powered, right? And I'll model that by saying that it is drawing a current I load. Okay, this I load is the current that is drawn by the circuit that you are connecting. So now this current, depending on the circuit, it can be very small or very high, right? So probably if you connect it to an entire receiver chain, it can take probably a few hundreds of milliamps or close to an amp also sometimes. So this current I load, where is it coming from? It has to come from the op amp like this to the supply. Okay. So now, as you will be knowing, or some of you might already know, the op amp needs a bias current so that it's operating in the required way you want. Okay. And I call this bias current as IB. And this bias current also depends on the current the op amp can deliver. Okay. So let us say if you want to deliver 10 milliamps of current, the op amp can burn say some 10 or 20 milliamps. But let us say you want to deliver 100 milliamps of current, even the bias current that the op amp needs will be proportional to that. Okay. So now this is let us say your requirement on this load current changes from 100 to 200 milliamps. But let us say you design the op amp only for load current of 100 milliamps. This might not work, right? So what you'll have to do is you'll have to design it for a very worst case scenario, and that's going to be not very efficient, right? Because you'll be unnecessarily burning current in the op amp. So what you don't want, so let me make it here. IB is proportional to the load current. Okay, so we don't want the op amp to deliver the load current. If you can arrange something like this, then you can design the op amp so that the bias current is small. Okay, and we'll try to make an arrangement so that the load current comes from some other place, right? And obviously, finally, it has to come from the supply, right? So let's say this is the supply. There is this. So what we want is, let me go to the next page. So this is the out. So earlier what we did, we simply connected the op amp output to the output voltage, and that was forcing the load current to be also delivered by the op amp. Now I don't want to do that. Okay, I want to provide some other path for this load current to flow from the supply. Okay, so okay, let us say earlier you connected it like this. What is the total current flowing here? Yeah, if I call it I out is what? I load plus the current that is flowing in this resistor, right? I'll just call it some IR. IR. Okay. Now let us say my load current is fixed, my output voltage is fixed. In principle, if I have a current source of this value, okay, if I'll call it probably I1, I1 is equal to I out, then V out will be the value you wanted, right? That's fine. V out will be say some V naught. That's what you wanted. Okay. So basically, what I'm saying is you don't need to have this portion, and if you just have a current source I1 that is equal to the load current plus the current required in this branch, then V out will be what you want. Okay. But as we just saw in the bandgap reference case, this I1 value will not be, we can't fix the I1 to be exactly what you want. So obviously I1 can be higher or lower. So if let us say I1 is lower than the output current required, what can you say about V out? This is I1. I'm saying that the I1 here is smaller than some of these two currents. Sorry, V out will decrease, right? Because earlier, let's say you had I load plus IR, you removed I load from here, the current IR was flowing in this branch and generating the output voltage. But now you have a smaller current, say some 1 milliamp smaller or something. But here the current you are pulling is same I load, so a smaller current will flow in this branch. So V out will also reduce. V out will reduce, right? So obviously you cannot keep it like this. What we need to do, we need to compare V out with the ideal voltage you want, right? And if you think about it, that's already being done here, right? For example, if this is V out, what is this? This is V out by K, right? And our V naught is K times V ref, right? So here I have V out by K that is compared with V ref. Okay. So now if this is the case, if I1 is less than V out, we know that V out decreases. So what should I do to the current to make V out equal to the nominal value? We need to increase I out. Okay. So based on based on this voltage, again we need to tune this current, right? So I1 again a voltage controlled current source, right? So based on this, you will tune this. Again, what is the simplest voltage controlled current source? MOS transistor. So here you might be tempted to put it like this. Okay, but let's quickly check once if this will work. If let us say you want to increase I out in this case, if I call this VG, what should happen to VG? VG must decrease. Okay, but in the case where I've shown, I know V out is smaller, right? Basically, V out is smaller than, V out by K is smaller than V ref, right? So if basically this voltage is smaller than V ref, so that's correct. Yeah, this voltage is smaller than this voltage. So what will happen to VG? Increase. No. You want VG to decrease, but in the circuit, if V out is smaller, that is V out reduces, this voltage will also reduce. So VG will increase, but that's not what you want, right? So we want to reduce VG. So what is the change I have to make here? No, this is the voltage controlled current source, right? Yeah, but if you put an NMOS, remember the source voltage is now connected to V out, right? It is not a very clean way. right? Because with the PMOS, your source is fixed. Thus, by tuning gate voltage, we can very easily control the current. But with the NMOS case, the source voltage is connected here. So even if you change this, source voltage will also increase. You might not be able to control the current so much. Okay, so PMOS is a better choice here because one end is fixed. So what other change you can do? Right? See what I want. If this voltage reduces, I want to reduce this voltage. Now it is increasing because this is negative and this is positive. Right? So I can simply swap the signs. Okay. So let me just draw the final circuit and finish today. So this is the final circuit. And this is positive and this is negative. So this is V out and this is the load current here. So now again, this is also a good regulator because if this varies, the op amp is forcing this voltage V out by K to be Vref. So any variations here ideally will not get reflected at this point. Okay? And the second thing problem we had was the load current. Now the load current is flowing here and the op amp can just draw the bias current required so that it operates in the required fashion. That's all. Okay. So let's stop here and we'll continue next.